Unit 4, Lesson 2, Special Triangles. So up until now, we've always used a calculator to solve questions that involve sine, cos, and tan, right? In the last lesson, we always punched those numbers into a calculator, right? Sine 30, sine 45, whatever the values were, we used our calculators. In today's lesson, I'm going to show you that it is possible to solve the trig functions for specific angles without using a calculator. And the reason why we can do this for certain angle values is because of these two special triangles. So you are going to be required to memorize these two triangles. So in our first triangle, it is an isosceles triangle because we have two sides that are both 1. And we learned in previous units that the angles underneath the equal sides are also equal. So this is 45 and so is this. Okay, so this starts off pretty easy to memorize. We have a right angle isosceles triangle. The two sides have a length of 1, and then the two angles underneath those lengths are 45 degrees. Not too bad to memorize. The only thing that we need to solve for right now is the length of that third side. Okay, and that's really easy. We're just going to use Pythagorean theorem quickly. Okay, so let's solve for that third side. So our value of a and b is 1. So we get root 2 for the length of that third side. Okay, so that is the first special triangle that you have to memorize. Okay, the isosceles triangle where the two equal sides have a length of 1 and the two equal angles of 45. Okay, you can also obviously figure out those angles by knowing that the sum of all three angles is going to be 180. So subtract the 90-degree angle from 180 and then divide the remainder by 2 and you'll get 45. That's the reasoning behind it. So the only tricky value for you to memorize is going to be this root 2. But again, you don't necessarily have to memorize it. As long as you know that these two sides have a length of 1, just use Pythagorean theorem if you forget what this length of C is, and you'll figure it out. So there's your first special triangle that you need to memorize. The second special triangle comes from an equilateral triangle. Okay, and I'm going to show you this because it might make memorizing this guy a little bit easier. So this guy comes from this triangle. It's an equilateral triangle, so right away you guys know that all the interior angles must be 60, right? Because we need three angles that add up to 1. And this equilateral triangle has side lengths of 2. Okay, so that's pretty easy to memorize. But then you might be asking, okay, well, how come this is the special triangle version of that equilateral triangle? Well, the way that they get that special triangle is they divide this guy in half. Right? Because if you divide this guy in half, you get this triangle, right? That bottom angle is still 60. This is going to be 90. This side is still 2. 2 divided in half is going to be 1, hence why we have the 1 down there. And likewise, this top angle was 60 originally, but when we cut it in half, now it's down to 30. So you can see how this special triangle comes from that equilateral triangle. And that'll help you in the memorization process, I think. So now that you know where all these values came from, there's still one that we need to figure out. And that's this guy right here. What's the side length there? So again, we're going to use Pythagorean theorem. Okay, so the side length B is root 3. So there's your second special triangle. Okay, so these two triangles, once again, are so important, and it's important that you are able to memorize these two triangles. Shouldn't be too hard if you understand where these triangles came from. Okay, so let's use these special triangles to develop the ratios in the following table. Okay, so basically we need to figure out what sine 30 is and put it here. What sine 45 is based on the triangles above and put it there. What sine 60 is based on the triangles above and put it there. And do that for each of these spaces in the table. So let's go ahead and do this one at a time. Okay, so first, what is sine of 30 degrees? Well, let's look at our special triangles. So pick the triangle that has 30 degrees in it, so this guy right here. And now what's the ratio that's associated with sine 30? Well, sine 30 is opposite over hypotenuse, so it must be 1/2. Okay, so now anytime on a test where I ask you to evaluate sine 30, you know that sine 30 is a half, okay? Let's try what's sine 45. Well, let's go ahead, pick the triangle that has a 45-degree angle, and then what's the opposite and hypotenuse side to that angle? So opposite is 1, hypotenuse is root 2. So that means that sine of 45 is 1 over root 2. So again, on a test, if I say evaluate sine 45, don't plug that into your calculator. You know from these special triangles that sine of 45 degrees is equal to 1 over root 2. And we're going to leave it like that as a radical. We're not going to have dust because these are exact values. Okay, let's figure out sine 60. Okay, so here's 60 degrees. So sine of 60 is going to be root 3 over 2. Okay, let's try cosine. So what's cos of 30 degrees according to our special triangles? Here's 30 degrees. Cos is adjacent over hypotenuse, so it's going to be root 3 over 2. Pause the video and fill out the rest of these spaces. Okay, so there is the final completed chart. These are all exact values that you're going to be able to use in future questions. The only thing I want you to be aware of is whenever you have your radical in the denominator. So for example, right here we have 1 over root 2. Root 2 is in the denominator. Same with right here, and same with right here. So there's 3 times where this comes up. Sometimes things like the textbook or other question write this a different way. Really what it comes down to is they don't like having the radical in the denominator. And you'll see why in later questions that actually does make it a little bit more challenging. So instead of writing the radical in the denominator, they multiply the ratio by 1, and that essentially brings the radical into the numerator. Let me show you what I mean. So let's look at sine of 45 equals 1 over root 2. We don't like the root 2 in the denominator, so let's multiply this by 1. So root 2 over 2 is the same thing as 1, right? So we're not changing the question. That's why we're allowed to do that. And watch what happens when we multiply this together. So 1 times root 2 in the numerator, that's just root 2. And then root 2 times root 2 is the root of 4, which is actually 2. So 1 over root 2 is the same as writing root 2 over 2. And you might see both versions. You do need to understand that root 2 over 2 is the same as 1 over root 2. Okay, cos of 45 degrees is equal to 1 over root 2. So again, we don't like that radical in the denominator, so let's multiply this by 1. So root 2 over root 2. Let's get that radical out of the denominator. So let's multiply these. So 1 times root 2 is root 2, and root 2 times root 2. Okay, so 1 over root 2 here is also the same as root 2 over 2. Let's do our last one, okay? We got root 3 in the denominator. We don't like that, so we're going to multiply this by 1. So root 3 over 3. It's the same as 1. Now let's multiply. So multiplying fractions, you multiply the two tops together, the two numerators. So 1 times root 3 is root 3, and root 3 times root 3 is 3. So 1 over root 3 is the same as root 3 over 3. Okay, so those are just a couple things to be aware of. So if you're looking at this table and thinking, oh my goodness, how am I supposed to memorize that? You only have to memorize the special triangles above, okay? If you memorize and understand those triangles above, you can produce these ratios on the spot. Example 2, determine the length of the unknown sides of the following triangles. And I should have added in there without using a calculator. Okay, so as soon as you see that without using a calculator piece, that means you should be using your special triangles. Okay, but when you look at this, you're thinking, which special triangle has a hypotenuse length 8? We don't have a special triangle whose hypotenuse is length 8. So we need to ask ourselves, which special triangle is maybe a scaled version of this one in the question? Okay, and the hint is look at the angle, right? We have a special triangle that has an interior angle of 30 degrees, and it looks like this. Okay, so this question is a scaled version of this special triangle that I've just drawn. The special triangle has a hypotenuse of 2, and our triangle has a hypotenuse of 8. So what's the scale factor between these two triangles? Well, it's times 4. So that means to find the length of the other unknown sides, we just have to multiply corresponding sides from the special triangle by 4. To find the length of the side across from the 30-degree angle, that one corresponds with the side length of 1. We need to multiply 1 by 4. So obviously this side length is 4 units because we multiplied this one by 4. Okay, so to find side C, all we did was we multiplied 1 by 4. Okay, let's find side A. So A corresponds with root 3 on the special triangle. So if we multiply root 3 by 4, we will get the length of side A. Okay, and we're going to keep this as an exact value. So the side length of A is 4 root 3. So now we know the lengths of all three sides. So sometimes it's just a matter of figuring out which special triangle the triangle in the question is a scale version of, figure out what the scale factor is, and then multiply each side length accordingly. Example 3, determine the exact value for the following expressions. And again, I'm going to say without using a calculator. So that means 1, you're going to use your special triangles because you can't use a calculator. And 2, we're going to keep them as radicals because I want the exact values. Okay, so one thing to note, there's some notation here. Sine squared 60 degrees means take the value of sine 60 degrees and square it. Okay, so let's do that. Look at your special triangles and figure out what sine 60 degrees is. And you're going to notice that sine 60 degrees is root 3 over 2. Okay, you get that from your special triangle. So root 3 over 2 is sine 60 degrees, and then in the question it's squared, plus tan squared 45. So what's tan of 45 degrees? Go to your special triangles. Tan of 45 degrees is 1, so we just have 1, and then it's squared. Now let's do the math. Okay, so root 3 over 2 squared is 3 over 4, plus 1 squared is just 1. So now we just have to get common denominators and then we're good to go. So the answer here is 7 over 4. So do you see how we can figure out this question without using a calculator because it involves angles that are found in our special triangles? Let's try this one. So solve this one without using a calculator. So we're going to have to use our special triangles. So sine 45 on our special triangle is 1 over root 2, or root 2 over 2. Okay, and I'm going to use root 2 over 2. And the reason why is because it's a lot easier to add something like that than if it was something like this. If I had 1 over root 3 plus 1 over root 2, and I had to add these, I'd have to find common denominators involving radicals. It's just a lot more difficult. That's why I suggested back when we were filling out the table to use the version of the ratio that does not have a radical in the denominator. Okay, so sine of 45 according to our special triangles is root 2 over 2. Cos of 45 according to our special triangles is also root 2 over 2. Sine of 30 according to our special triangles is equal to 1/2. And sine of 60 using our special triangles is equal to root 3 over 2. And I'm going to recommend that whenever you guys are writing a test, the first thing you do before you even start the test is at the top of your page, draw out your special triangles and label them, okay? And then you can always refer back to them throughout. And then once you have those drawn on your page, you don't need to think about it. Okay, let's do the math. So let's multiply the first two fractions together. So root 2 times root 2 is 2. 2 times 2 is 4. Plus, multiply your numerators together. 1 times root 3 is root 3. Multiply your denominators together. 2 times 2 is 4. Now they have common denominators already, so let's go ahead and add these fractions. Okay, and that's your final answer, right? We can't combine 2 plus root 3 because they're not like terms, and we don't want to simplify root 3 because we lose some accuracy. All right, example 4. Using exact values, so using our radicals, no decimals, prove that 1 plus tan squared theta is equal to 1 over cos squared theta if the angle value is 60 degrees, okay? So we need to solve and show that these two expressions are equal. So is 1 plus tan squared theta the same as 1 over cos squared theta when theta is 60 degrees? So before this lesson, before learning about special triangles, you would have plugged in 60 degrees in for theta, and then you would have plugged this into your calculator. Now that we have special triangles, I want you to move away from doing that. We can solve this using our special triangles and using exact value, and I'll show you. So let's plug in 60 degrees into the equation. And now let's use our special triangles to solve this so we don't have to use a calculator. So what's tan of 60 degrees using your special triangles? It is root 3. Okay, and then we just square it. What is cos of 60 degrees? 1/2. And we're going to square that. Now let's simplify. Root 3 squared is 3. 1/2 squared is 1/4. Okay, let's simplify again. So 1 plus 3 is 4. 1 divided by 1/4 is the same as 1 times, take the reciprocal, so 4/1. And we'll simplify this. Okay, so since the left side equaled the right side, we can conclude that 1 plus tan squared theta is indeed equal to 1 over cos squared theta.